Please big a very big round of applause to Alex Bayan.
Hi, it's a real pleasure to be here. Thank you to the organizers for the invitation. Today I'm going to talk about the future of mixed autonomy traffic. And we just heard about science fiction. We're dreamers. The future of transportation could be multifaceted. It's not clear whether we're going to have flying taxis, whether we're going to have CarTube, the Boring Company, Hyperloop, e-taxis, and many other things. And in fact, when people look at what the future of transportation might look like, they really wonder, with self-driving vehicles, are things going to get better or worse? In fact, the US Undersecretary of Energy, Ruben Sarkar, used to show this graph from Don McKinsey from UW, showing that, in some cases, you could see a future with improvement of 60% of the energy footprint of mobility, you going to work, shopping, or whatever you're doing, or things could get worse by 200%. And we don't know where we'll be on that graph. And the reason is, think about it for a minute. If you platoon cars with automation and try to boost the capacity of the freeway lane by having people go 150 miles an hour 2 or 3 feet from each other because it's enabled by the technology, well, maybe you improve congestion, but you burn more gas. On the other hand, if you send your empty self-driving vehicles pick up your children at school, you might have a freeway packed with people with cars with nobody in there. Or you might find yourself in a situation where cars are just circling to find parking. So part of the work that we need to do as engineers in a society where we need a lot of transportation is understanding beyond the automation, beyond the car manufacturing, how we're going to be able to deal with these hundreds of thousands of vehicles. So this talk is not so much about how we make the next car drive or fly. There is a lot of companies that work on building the next feature of automation. There's 5 levels of automation, and some are closer than others. And you can do some things like falling asleep in your car, not a very smart thing to do, maybe better to do in 10 years. That's not what this talk is about. This talk is about how we take hundreds of thousands of these vehicles and make traffic better and make mobility better. And throughout history, engineers have taken that problem and tried to solve it in many different ways by building models, mathematical representations of what mobility looks like, and try to model things at different scales, whether you model them at the scale of an individual vehicle, an individual person, or small set of vehicles, or the level of an intersection, cars crossing, or maybe the level of a district, or city or set of cities, maybe 500,000 to 1 million vehicles, or something like the Los Angeles basin with millions and millions of vehicles. And of course, for each of these, the models are different. If you're modeling energy consumption of a single vehicle, you can afford to model everything all the way to the engine, the physics. But if you're modeling a whole city, maybe you can't, because at least until a few years ago, you did not have the computational power to do it. And so the no big deal state of the art today, I apologize for this, is, let's see. Today, it's pretty easy and standard to do simulations like this one. It's a micro simulation that models the impact of apps like Google, Waze, and Apple Traffic with hundreds of thousands of vehicles. That's not a big deal. That's something that 10 years ago you couldn't do, but nowadays you can do this routinely. Of course, you need data. You need to calibrate it. So that's where it connects with this crowd here. This, 10 years ago, you couldn't really do. Now you can do, it's not a big deal. The question is now, how can you use this inside AI to optimize and make things better? And for that, there is roughly 4 barriers that we collectively as research community need to overcome. One of them is data. We need data. If you want to build a model of Las Vegas, if you want to build a model from Los Angeles, you need to understand the flow of people, where they're coming from, where they're going, where they live, and so on and so forth. Then you need to calibrate models. Like people on the strip drive at a specific speed, but next to where I live, they'll drive at a different speed. You need to understand their routing patterns, and these are changing because you have apps, and these apps, like we just heard with Alexa, they tell you where to go, and so that's changing over time. Then there's the model computation, which I just showed. The fact that if you want to simulate all the vehicles in Las Vegas, you can do it, but it will take a certain time, even if you're not on the cloud. And finally, there is the control and the optimization and how to make things better. And so it's hard to see where the future is going, but I'm not going to worry about the data. Someone has the data. Google has the data. Apple has the data. We heard 75 billion connected devices soon on the planet. So that data is somewhere, and whoever will be in charge will have access to that data. So this talk is not about the data. The talk is about calibration and other things. For example, making a model work at scale, that's not easy. That's because the search space for these types of problems is quite enormous. Computation of the model will also be a challenge, because ultimately, if you want to have a really detailed model, it will cost something. It's not something that you can run in seconds. But mostly, the challenge is in the learning and the control. And so this is where the program here we have launched at Berkeley essentially amounts to understanding how, over the next 2 or 3 years, we can create capabilities to do that. And what is that? That is essentially the ability of blending 3 main components. One is microsimulation. The microsimulation is essentially philosophy or approach or technical approach in which you can model every vehicle second by second, so microsimulation, with AI on the cloud. If you have that, essentially, and if you have the ability to scale that, then every city in the world can benefit from it and start running things at scale that is relevant for them. That's a capacity that almost no city in the world has today. So this is our agenda. This is where we need your help. This is where we want to engage with the community. And if we reflect about why now, why this, and why are we going to have a major disruption, people have been interested in this problem for decades. The first historical measurement of a traffic jam goes by to 1935 with the work of Bruce Greenshield. In Ohio, there was some kind of an agricultural festival, and the road was small. Maybe a couple hundred people showed up. That created a traffic jam. Nobody had seen that before. A guy stood there and measured traffic. That was the first time someone ever measured a traffic jam. Time passed on. People used that. People came up with equations, models. And at the time, you have to realize this is the 50s. People believed in physics, in laws that model the physical world, equations that can describe how people move, equations that can describe how shock waves move. The world went on, and then in 2008, someone came up with this experiment, which I'm sure many of you have seen on YouTube. So you ask a bunch of humans to drive in a circle at 25 miles an hour. I'm sure you can do that. It's not that hard. Except if you have people do that long enough, what you will see is that traffic breaks down. It's actually not that easy. So stop-and-go waves happen. That's because humans are not good at that. You've probably heard of jammetons, phantom jams, stop-and-go waves. These are all fancy names that many universities throughout the year came up with to describe these problems. When you're on the freeway and you're stopping for no good reasons, that's the reason. It's because humans are not good at self-regulation. Something that self-driving vehicles will probably fix. That was 10 years ago. Hundreds of research articles were written on that topic. 10 years later, a person ran that experiment in Arizona last year, Dan Work, Cal grad. So this is a video, and you can see this arrow as a car. That car is currently driven by a human. So you can see this stop and go and stop and go and stop and go. And at some point, the arrow will turn red, which it does now, which means now the car is self-driving. And what do you see? It's all smooth. So one single self-driving vehicle in that ring enabled to regulate the flow and enabled 42% savings in energy. It's crazy, right? 42%. On the freeway, probably the equivalent of this would be 10%. If all of us could save 10% of energy, it's good. Like we heard AI for good. This is a very good example of what AI could do. So a year later, Kathy Wu, who is a professor at MIT, came up with something similar, which I'm going to show you. And so same setting. So the red car is a self-driving car. Right now it's not self-driving. The blue car is what it can see. It can see the car in front of it. And the white car is just a car driven by a human. So first, nothing happens. So you can see the stop-and-go wave because there's no algorithm. And at some point now, it's going to turn on the machine learning, and it's going to regulate traffic. And it's smooth. What's the difference between this movie and the previous movie? The previous movie used a physical model of every vehicle. And it took that model in the algorithm it devised. In other words, it figured out, OK, a car drives like this, a human behaves like that. Because of this, I can optimize this way. You pose it with your favorite optimization program. You solve it, and it gives a result. This has no model. This has been achieved by a clever use of deep reinforcement learning, in which you simulate on the cloud over and over and over again until you generate a policy that can do exactly the same. So you could argue, well, what's the big deal? It's a very big deal because this is the beginning of a new era in which you might not need a physical model, and therefore you might not need an expert knowledge of a specific field to improve it. And if you think about the academic production that went into this, between the very first measurement of traffic jams in the 30s and 2008, there's over 10,000 papers written on this. People became very famous by inventing words, jammetons. Between the first experiment and that second article, and the ring experiment that was run in Arizona, there's probably 1,000 articles. And then it took one machine learning algorithm to redo the same with no model. And so what I'd like to do now is to walk you through a set of, sorry, this keeps jumping on me, of Lego blocks to try to see where this is all going to go. And all of the movies you're going to see in the next 5 minutes have the same color code. Red car is self-driving. Blue car is what it can see or sense through connection. And white car, it doesn't know it's there. It's just a manned vehicle. So first experiment for fun. This experiment. So you can see this kind of red car is behaving like a jerk, right? It's essentially preventing the guys from behind. You can imagine there's a lot of horning in the software, OK? And it's managing to do the same, 2 rings. Again, no model. That's the beauty. Nobody has ever managed to write the equations for this in a way that is actually robust enough to make this work. But the exact same code for 1 ring worked for 2 rings. And you could argue, what's the big deal, right? You learn this in police academy. So you all kind of learn, you taught a computer to do what people teach in police academy. Well, not a big deal. OK. So of course, this is the beginning. So the next thing is, what about intersections? So think about intersections. So take a simplest intersection you could think about, an 8-figure like this, and just let humans deal with it, OK? What happens is like, please, you go. No, please, you go. No, you go. No, you go. Okay, right. This is probably the most inefficient way of dealing with an intersection. In fact, if you go to work and you have a stop sign, you know this, because it's just a nightmare. All right, so now imagine you use the same paradigm, and you essentially try to leave the AI deal with it. What it does is it actually does a snake. It learned to create a snake. You didn't teach it what a snake is. In fact, there is no model for it. All it's doing is deep reinforcement learning. So it keeps doing simulation until it figures out something to do. And here, it learned to do it in a way that is pretty clever. It figured out the right speed at which the spacing between the vehicles would enable the snake to be as long as possible so that you don't have to stop, which is the best way to maximize the efficiency of that intersection. Same code. But I can still explain to you what it's doing now, right? I mean, I kind of, if I was teaching this in class, I would probably pretend I've worked on this all my career, and this is a super clever solution, and I can find a good explanation for it. And if you look at the trajectories, it's pretty cool. It essentially has figured out how to platoon vehicles. You can see these trajectories, depending on the direction, and instead of having them cross each other, it platoons them. So it's pretty clever. OK, now take something a bit more challenging. So this is now, there's a routing issue here, because you can go the short loop, you can go the long loop. And what you're trying to do is you're trying to maximize the efficiency of that intersection. So it's something a bit more complicated. So if there is just manned vehicles, there's some politeness. Please, you go. No, please, you go. Please, you go. There's a typical politeness problem. And now, if I try to see what AI would do here, what it would do, if the movie allows me to start. OK, let's see if we will have technical problem. Apologies here. Let's see. All right. So now sim, we have a self-driving vehicle, and you can see some of the vehicles behind it or in front of it. And sometimes it stops, and now it goes. It'll go for a loop, and it'll stop again. And frankly, I have no idea what it's doing. And that's the point. At that point, it's not that complicated. It's a double ring. Even my son can build this in Legos. But I cannot even explain to you what it's doing. It figured out that in some cases it should learn to stop. In some cases it should go. You look at the throughput, it's clearly more efficient, but I cannot rationalize anymore. This is where AI has now essentially superseded more than half a century of human research on how to model these things. There are people who spend an entire career modeling these things. And so now you can get with it. I can go a bit faster. So we're going to build a bunch of Lego blocks to see, could you scale this to the level of a city? And then all the beautiful things you just heard about in this conference and in the previous talk, such as transfer learning, typically apply here. What if you taught it to do something on the ring and then put it in a situation which has never seen before? You can do it. You can show that the algorithm converges. And so this is an example of a single merge. Here, so typical problem, you have people merging into a road that creates a shock wave. The shock wave back propagates, and then you slow down and speed up. You can see these waves happening here. Okay? So what if you actually do transfer learning to deploy the policy you learn on the ring, where you learn to stop or to slow down, and apply it to the merge, where you can see these shock waves propagating here. So that's what it would look like. So you can see once in a while there's a red car. It's a self-driving car. And when these shock waves happen, you'll see them happening, it will preemptively start to slow down to try to smooth them. And when things get much worse, like now, it's actually holding people. So it's essentially the car has invented a red light. It's kind of a strange statement, but that's what happens. And it has never seen that situation before. It learned to do it on the ring and somehow figured out that's the right thing to do on the merge. So that's a very interesting example of transfer learning. And the other interesting part here is that it can also be done with a very small number of self-driving vehicles, which is very promising. I mean, we're not going to have 100% self-driving vehicle in the near future, but we are going to soon have a situation in which a few, maybe 1%, 2% have automation features. This is an example of what the trajectories look like. In the left plot, you can see the shock waves due to this kind of stop and go. And in the right plot, you can see the preemptive deceleration that the self-driving vehicles can apply. And so when I showed you the initial graphs of, will self-driving cars make things better or worse, that's the kind of work you can do. Is like, how many automated vehicles would you need to smooth traffic? And right now, what the numbers show is that with less than 10%, you can probably smooth these waves and save a lot of energy. This was featured in Science magazine last week, and Abudi, who is sitting here in the second row, was the lead author on these penetration studies. So of course, where are we going with this? We're interested to see if, can we use all these Lego blocks to really tackle challenging problems. Like this is a micro simulation of the Bay Bridge in San Francisco. If you've driven through that bridge at commute time, it's your worst nightmare. That's going to definitely make you miss your meeting. And the point is, the only thing there is to make things better here is that green line, which is the metering light at the bridge, which is the only way for the last 30 years. By the way, UC Berkeley came up with the first algorithm that was ever implemented this in the 70s. But that's the only thing you have at your disposal to make things better. So what if instead you used a small proportion of self-driving vehicles to hold the flow? On the top part, there's essentially a bottleneck that clogs the bridge or the merge. Here, if you just hold people preemptively, you can keep the bridge flowing. And so that's the promise of deep reinforcement learning. But the reason why now and why this way and why at this scale is because the takeaway message is you don't need a model anymore. You don't need to model all these lane changes and accelerations and human behavior. All you need is a software that can model it. You don't need to look under the hood. And then deep reinforcement learning will do it for you. And essentially now, the process is how do you build these Lego blocks to combine them so that by creating an assemblage of them, you could tackle situations which are a lot more complex. So it's all very nice. It's all in simulation. And at some point, something needs to happen in the real world, and we saw a self-driving car experiment before. And so the first step to try to see how far we can push this transfer learning is to see, could we potentially apply this on hardware? And so together with our colleague Andreas Malikopoulos from University of Delaware, we used as a first kind of a more realistic case what they call Minicity. Minicity is a replica city that they built at the University of Delaware. By the way, they have a really good French cafe. I just put it on the top right. You probably noticed from my accent I'm French, so I'm very attentive to these details. I was part of the selection process finding a test bed which has a French cafe, so that one has one. And so you can, essentially that's a really cool test bed because you can drive these mini cars remotely, and then you can have either humans drive them, or you can have a model of the human drive them, and then you can interface it with another of them, which has a self-driving car feature. So essentially, it's a way in the lab to simulate self-driving vehicles and their interactions with humans. And so here, what we wanted to do with that specific example is just look at that little roundabout here and figure out whether we could apply the same algorithm. Again, the notion being you'd learn it in the software, and then you deploy it in the field in order to see if it works. And so this is an example of what that simulation would look like. Kathy Jiang and Eugene Vinitsky were the two students who did this. So you'll have two movies here. On the left, you have no machine learning. And on the right, you have the deep reinforcement learning approach. The blue cars are automated. And essentially what it's trying to do is it's trying to flush all the cars as fast as possible throughout the intersection. If you focus your attention on the Hummer vehicle on the right, that's the last vehicle that will exit that roundabout under the machine learning scenario. But on the left, you can see that by the time the Hummer has exited on the right, there's still vehicles in the roundabout. So simple example. But here the point was to show that with these types of policies that are learned in the software, you can essentially improve the efficiency of that intersection, even though the system has really not seen it before. And furthermore, you can demonstrate the transfer learning by showing that you learn in one environment and demonstrate it in the other environment. And so that raises another interesting question, which is, actually, we still have access to the state space. And if you don't know what the state space is, it's like a simple word to describe the position of the car, the velocity of the car, the acceleration of the cars, and all the onboard parameters. So still, we don't know what's happening under the hood in this paradigm, but we still have access to the position and speed and acceleration and state of all the vehicles that we're interested in. What if we also decided to remove that? And so this is the notion of, when you do deep reinforcement learning, you take actions, and you get rewards, and that's based on what the state space is. That's ST. So every iteration cycle, you do a better action. If you do well, you get a better reward, and you have access to the full state space. What if instead you got access to a picture of it? What does that mean, a picture of it? Picture of it would be, what if instead of knowing the speed, location, acceleration, all this, you just saw it? So it's like back in the days when they were learning to play Atari games with Q-learning just by looking at the screen. What if you did the same with the vehicles? And furthermore, what if you also only use this in the way you were computing your actions and in order to get better rewards? So that's called pixel learning. And the beauty of it is that that can be done. And so you look at Minicity, so going back to the same map as I showed before. On the left, you can see a simulation of the city. So it's quite complex now. There's a bunch of moving vehicles with different types of routings and so on and so forth. And then we can ignore the right for now. So the next thing we showed with this is that everything I've shown you before, we actually can do it by just looking at the movie of traffic. That's another paradigm shift. 20 minutes ago, I told you, we get rid of equations because we don't need these models anymore. Now I'm telling you, get rid of the state space. Just look at the movie. And so that's going to be the next paradigm shift, be able to do the same as we have on the left. And then to push it even further, it's not realistic to assume you'd be flying an aircraft over the city and looking at the city all the time. So what if you actually only were able to look in your surroundings? So in other words, I'm a vehicle, and I can sense the other vehicles. I can maybe see it. Can I redo the same? And that's the edge right now. We believe in 2 months we will be able to demonstrate that all the other things I've shown you before, the bridge, the crossing, the rings, and all these other maps, we can do it, but we can do it by just looking at the image of traffic. And that's something which in the transportation engineering community has never been done before because it's new and because it's also not something that was possible 5 years ago. And finally, if you try to push this even one step further, then the last bridge with this community and machine vision is, what if you could actually do the same, but now instead of this, use segmentation image? So essentially, all these Nextcar and Dashcar cameras that you can put on your vehicle, or all the onboard avionics of the self-driving vehicles, that actually produces images that can be, with supervised learning and many other techniques, essentially segmented, from which you can infer the position of the vehicles, the speed of the vehicles, their trajectories, and many other things. Ultimately, that is going to be the source of data. When we just heard in the previous speech, this 75 billion connected devices, in 5 years, every vehicle coming out of factory will have this, and will have the ability to see its surrounding, which means if you plug it back to all the things I've been telling you over the last 20 minutes, we can then learn from these pictures, and we can then learn the models at the scale of the city, and then we can optimize it at the level of the city. And of course, there's a bunch of ifs here. There's a bunch of things which are complicated, because to learn, you need to be able to screw up many times. But I cannot every day come to Las Vegas and try to screw up traffic to learn how to do it well. That will not be allowed. So obviously, there's a lot of hurdles to be overcome here. But I think this is really the way traffic management in the future will be essentially disrupted and revolutionized. And so to finish the talk, essentially, it's a good opportunity for me also to thank AWS and Amazon for their support, because one of the things we were able to do is to essentially integrate these three things I talked at the beginning of the talk. A traffic microsimulator, which is, again, something that 10 years ago you could not even run at the scale of a city, but now you can, with state-of-the-art deep reinforcement learning libraries, RL Lab, and things produced at Berkeley, on the cloud, the AWS cloud. That is probably one of the major ingredients that we want to push forward to the municipalities, the cities, the metropolitan planning organizations, to have them plan. It's not that far. Within the next 5 years, we will see Los Angeles-wide simulations and optimizations that include optimization of traffic lights and self-driving vehicles and many other assets, things that weren't possible earlier. And the reason why it's possible now is this convergence of cloud computing and AI and state-of-the-art modeling and data, these 4 frontiers I showed earlier, that together bring this new component. And that's the exciting part, because again, you could argue that level 2, 3, 4, 5 in automation of vehicles, it's getting there. Car manufacturers are working on theirs. This is a super crowded space. But the space here of how you coordinate these hundreds of thousands of vehicles in a way that is more efficient, that's the beginning of a new era. That's an emerging field. And that's why it's a field which is very exciting to be in. And so this is my last slide. The one thing that I'm really excited about is, just like many of you are used to the Mujoko benchmarks, I'm sorry, it keeps going back and forth, we put together a set of benchmarks in this open platform that you can all download. And just like you were, like when the Mujoko humanoids start to learn to walk, the same is going to be available now for vehicles. If you live in a city and you want to make things better, either that benchmark already exists. If not, you can put that benchmark in our system, and then you can benchmark your algorithm against the rest of the world. And that's, in a sense, the openness we want in this field. I think you want to help cities, you want to help mobility, which means you need to have an open platform. You need to have a platform that is universal, that everybody can use, regardless of where they are. And you want a platform where people can contribute and build the benchmarks. This was released at Coral last month. We're going to keep building benchmarks. We hope that many of you will engage and also build your own benchmarks. And finally, as we build community for this, one of the things we are starting to do is we're starting to do workshops and training sessions, because a lot of the planning organizations that are in charge of mobility are in desperate needs of these technologies. And so with this, I'm going to finish my talk. I would like, again, to extend my warmest thanks to Amazon for the invitation. I'm really honored to be here, and it's really fun to be at this conference. Thank you.